So I want to go over in this video the payoff phase of glycolysis. This is basically starting in the middle of glycolysis at step number 6, and we're going to then go through to the end of glycolysis to pyruvate, or the formation of pyruvate. Now, step number 6 in glycolysis is an oxidative and phosphorylation step, and part of what's going on is in the oxidation that we're going to perform, we're going to capture some of the energy in the form of a the addition of a phosphoryl group to our substrate. So basically the enzyme that's catalyzing this step is our glyceraldehyde 3-phosphate dehydrogenase. Now, even if we couldn't recognize oxidation taking place, we got a big clue right here that we should be able to say, if you see this enzyme, dehydrogenase, you know oxidation is taking place. And of course, if you see a phosphoryl group being added to a substrate, then you know that you've got phosphorylation taking place. Now, another clue that we have oxidation taking place is that we have reduction taking place. Where is the reduction taking place? Well, basically, we have the formation of an NADH. This will be what we refer to as a reduced coenzyme. This is what we call these guys in the biochemistry business, and that is a reduced coenzyme. So what we're going to do basically is we're oxidizing the aldehyde, and the oxidation of this aldehyde yields such high energy that some of its energy is going to be preserved in the form of the formation of an acyl phosphate. So here we get an acyl phosphate. So some of the energy of oxidation of this guy goes here, and some of the energy of oxidation goes here. So we're going to oxidation yields energy, and that's one of the things that we're going to repeat a number of times, but you see energy coming from the oxidation reaction, and we're going to store some of it here, and then we're going to store some of it up here. Okay, now this is also again an NAD dependent dehydrogenase, and so basically we have that going on. Now, another thing I just want to remind you, remember that starting here from 1 glucose, we have 2 of these guys being oxidized, and we have 2 of these guys being reduced to give us 2 NADHs, and we get 2 of these. Now, of course, at the same time, we have to use 2 of these, but the idea is from each glucose, from 1 glucose, we get, at this point, everything that we get is going to be doubled per glucose. So at this point, we get 2 NADHs per glucose, and that's one of our energy recoveries. Now, we're going to go on to step number 6. And step number 6 is what we refer to as a substrate level phosphorylation. And this is important, an important distinction, because we have different types of phosphorylation. We have substrate level phosphorylation, and we have oxidative phosphorylation. And so this is an example of a substrate level phosphorylation, where we're going to take one of our substrates is ADP, one of our substrates is the 1,3-bisphosphoglycerate, which we got from a previous step, where we oxidized the aldehyde and added a phosphoryl group to it. And so here we're basically going to form ATP. One of our components of our buffer will be magnesium, and that's just basically to the ATP is typically going to be bound to magnesium. We typically have a magnesium +2 ion basically kind of bound here at this place in the ATP. And now we get a 3-phosphoglycerate, what have we done? Well, we've actually broken this acyl phosphate bond and stored the energy in the form of ATP, but we've completed the oxidation of the aldehyde. So basically, in essence, in steps 6 and 7, what we're doing is we're taking an aldehyde and we're oxidizing it to a carboxylic acid. Okay, so that's in essence what we've done. We've oxidized the aldehyde to a carboxylic acid, and in the process we used two of these, produced 2 of these, and 2 ATPs. So now we have basically produced 2 ATPs for each glucose that entered the pathway, and we actually are a little bit ahead because we produced NADH in the previous step. So at this point we've actually broken even. We have 2 ATPs that basically equal the 2 ATPs that we used, but we're not done yet. So we're actually going to process this 3-phosphoglycerate a little bit more. We've got 3 more steps, and we're going to prepare this molecule, basically these 2 molecules of this, for the citric acid cycle. So at this point, we've broken even. Now we're going to go and prepare our substrates to enter the citric acid cycle. So step 8 is what is known as the mutase reaction. It's basically another isomerization type of reaction, but the particular enzyme that carries it out is called phosphoglycerate mutase. Basically, in this reaction, our 3-phosphoglycerate is going to get converted to 2-phosphoglycerate, and it's basically just involves the movement of this phosphoryl group up to carbon number 2. Now, it turns out that this reaction is catalyzed in the enzyme, and the enzyme itself has a lysine, and the lysine, as you know from our previous discussions, has a positive charge, typically at physiological pH, because lysine has an amine side chain. So our lysine is in the binding pocket. Then the substrate comes in, our carboxyl group with a negative charge gets positioned near the lysine. Then our middle carbon, our hydroxyl carbon, comes next, and then we have our phosphate. And so our phosphoryl group is attached here. This would be our 3-phosphoglycerate. Now also in the active site of this enzyme is a histidine. And it turns out that this histidine has the ability to phosphorylate and be phosphorylated. So the histidine, and I'm just going to draw it, we'll just draw it as a his without drawing the ring structure. It'll be a little bit simpler. But when the substrate binds, the histidine has a phosphoryl group attached to it. And so the way this enzyme works is that in step 1, the phosphate basically attacks the hydroxyl, and then we get basically the addition of the phosphoryl group in step 1. Then in step 2, we have the phosphoryl group coming off of the substrate back onto the histidine. So basically, the mutase reaction, the way it works, is the enzyme transfers a phosphoryl group onto the substrate, and then for a moment we have a double phosphorylated glycerate. And actually we've encountered this guy before. The intermediate in this reaction is known as 2,3-bis-phosphoglycerate, or 2,3-BPG. It's the same molecule that helps to regulate our hemoglobin. So 2,3-bis-phosphoglycerate, remember, it's highly negatively charged with two phosphates, binds to the center of hemoglobin. Well, that's the same thing that is the intermediate in this reaction. It turns out that you actually need a small amount of 2,3-BPG made in order to phosphorylate the enzyme. So the enzyme initially can be phosphorylated by the 2,3-BPG, and then the phosphorylated form of the enzyme can react with this 3-phosphoglycerate to catalyze the phosphoryl group transfer. So the mutase reaction is basically a phosphoryl group transfer from the enzyme onto the substrate and then from the substrate back. So you're just trading off phosphate. So in other words, literally what does not happen is this same phosphate does not move up here. This phosphate comes from the enzyme, so this goes to the enzyme, and this one comes from the enzyme. But they're not the same phosphate. Okay. Now, step number 9, and part of what we're doing in this previous step is this movement of the phosphate or the phosphoryl group to another location is for the purpose of the next two steps. So basically these steps are they're all related to each other and they build on each other. So the mutase reaction moves the phosphoryl group to this new location. But what this location of the phosphate does is it serves to stabilize what's going to form in the next step. So in the next step, we actually have a step 9 is a dehydration reaction. And in this reaction, basically we have the loss of water and the formation of an enol. So this phosphoenol, basically the location of the phosphate here helps to stabilize the formation of this phosphoenol. And in essence, what it does, it redistributes the energy within the molecule. So the movement of the phosphoryl group up here rearranges electrons within the molecule, and then the enol form has a higher energy of hydrolysis for the phosphate. So if we had hydrolyzed the phosphate in the other location, we would not have had as high of an energy of phosphorylation. But what this movement, this phosphate in this location, basically this phosphoenol is going to have a very high energy of hydrolysis. It turns out that the delta G standard of hydrolysis for this, let me just write it like this. Whoops. Go back. Hydrolysis is equal to about -62 kilojoules per mole. Now that's a very, very large standard free energy change. And by forming so basically having the phosphate up here is important, but it turns out that forming the enol is very important for this large free energy change to be possible. Because if we were to hydrolyze this one, the delta G of hydrolysis for it is only -17 kilojoules per mole. Now, if we were to convert this to pyruvate, we are not going to have enough energy to make ATP. But by carrying out this dehydration reaction, we rearrange the energy within the molecule. This redistribution of energy leads to this large standard for energy of hydrolysis, which allows us then to drive the next reaction forward. So, moving the location of the phosphoryl group in step 8, dehydration in step 9, basically both of those steps together allow us to carry out the next step, which is basically couple the hydrolysis of this bond right here to the formation of ATP. And what we'll wind up with is the formation of pyruvate. So here we have our phosphoenolpyruvate, and we have ADP, our two substrates. And we have, again, this is another substrate level phosphorylation, so we have step 10. Is our second, let's put that in here, second, substrate level phosphorylation. And so here we're going to basically take the energy of breaking this bond and store it in our ATP. So about half of the free energy change is going to be stored in the ATP, right? So here we're going to store about 30.5 kilojoules per mole. And the remainder is going to give us a very large negative free energy change, which helps to drive this reaction forward. So this is a driving force. And it basically drives, that's an E, reaction forward, and makes this a metabolically irreversible step. So the 8, 9, and 10 in essence are coupled together. They couple together at least in purpose. So we carry out these steps so that we drive this reaction forward, and ultimately we prepare our pyruvate, and this will then be the substrate for another reaction that will then enter into the citric acid cycle. So we're at the end of glycolysis here, and we are prepared now to go into the citric acid cycle once we carry out one step. We'll talk about that step of conversion of pyruvate to acetyl-CoA. We'll talk about that in the next chapter, so we'll come back to that later.